Okay, we're now at section 16.7, energy in a capacitor. And okay, as you know, a capacitor can store energy. If the plates of a charged capacitor are connected by a conductor, like a wire, for example, charge transfers from one plate to the other until both plates are uncharged. Sometimes you can see this discharge as a visible spark. If you accidentally touch the opposite plates of a charged capacitor, your fingers would act as a pathway, and you would get an electric shock. Where high voltages and large quantities of charge are present, as in the power supply of a television set, such a shock can be fatal. So, in other words, be careful. Capacitors store electrical energy, and that energy is the same as the work required to move charge onto the plates. If a capacitor is initially uncharged, meaning both plates are neutral, the plates are at the same potential, then very little work is required to transfer a small amount of charge, delta Q, from one plate to the other. Once this charge has been transferred, a small potential difference appears between the plates. So work must be done to transfer additional charge against this potential difference. Let's take a look at our work equation again. If the potential difference at any instant during the charging process is delta V, the work delta W required to move more charge, delta Q, through this potential difference is given by this equation. We know that delta V equals Q over C. We know that delta V equals Q over C for a capacitor that has a total charge of Q. If we plot voltage versus total charge as shown in the figure, we get a straight line with a slope of 1 over C. The work delta W for particularly delta V is the area of the blue rectangle right there in the middle of that graph. If we add up all the rectangles, we can get an approximation of the total work needed to fill the capacitor. In the limit, as delta Q is taken to be infinitesimally small, the total work needed to charge the capacitor to final charge Q and voltage delta V is the area under the line. This is just the area of the triangle, 1/2 the base times the height. So we can write the work as shown here. W equals 1/2 Q delta V. Okay. As you know, W is also the electrical energy stored in the capacitor. From the definition of capacitance, we have Q equals C delta V. So we can express the energy stored in the capacitor 3 different ways. The potential energy of a capacitor is 1/2 Q delta V, or 1/2 C delta V squared, or Q squared divided by 2C. Let's do a quick example and calculate the amount of energy stored in a 5 microfarad capacitor when it is connected across a 120 volt battery. The potential energy in this case is 0.036 joules. In practice, there is a limit to the maximum energy that can be stored in a capacitor. At some point, the Coulomb force between the charges on the plates becomes so strong that electrons can actually jump across the gap, discharging the capacitor. For this reason, capacitors are usually labeled with a maximum operating voltage. Let's go through that. Potential energy of the capacitor is 1/2 C delta V squared is 1/2 times 5 times 10 to the 6 minus 6 farads times 120 volts squared, and that's how you get your 3.6 times 10 to the minus 2 joules. Okay, large capacitors can store enough electrical energy to cause severe burns or even death if they are discharged so that the flow of charge can pass through the heart. If you look at an experienced electrician, they always handle stuff with just one hand. They never handle it with 2 hands, where you can create a circuit from one hand to the other that passes through the heart. So an experienced electrician will only use one hand. Capacitors can also be used to save lives by stopping cardiac fibrillation in heart attack victims. When fibrillation occurs, the heart produces a rapid, irregular pattern of beats. A fast discharge of electrical energy through the heart can return the organ to its normal beat pattern. Emergency medical teams use portable defibrillators that contain batteries capable of charging a capacitor to a high voltage. In this case, as in the camera flash, the lasers used for fusion experiments capacitors serve as energy reservoirs that can be slowly discharged and then quickly discharged to provide large amounts of energy in a short pulse. The stored electrical energy is released through the heart by conducting electrodes called paddles placed on both sides of the victim's chest. The paramedics must wait between applications of electrical energy because of the time it takes the capacitors to become fully charged. The high voltage on the capacitor can be obtained from a low voltage battery in a portable machine through the phenomena of electromagnetic induction, which we will study in a later topic. That ends this section. The next section we'll cover is 16.8, capacitors with dielectrics.